All right, so this week we want to introduce Cesar Gonzalez Garcia. Cesar is an archaeoastronomer who works in Spain and Santiago de Compostela. Springtime. Working at INCIPT. So Cesar has got quite an extensive background, particularly in archaeoastronomy. We focused the last seminar on looking at how we go about measuring alignments and things of that nature. But one thing that we haven't talked about or discussed at all are some of the statistical methods that we utilize to analyze this kind of data, to understand what we're talking about when we start looking at different alignments in large data sets. Cesar has very kindly agreed to get up at the crack of dawn from Spain to come speak to us and give us our seminar. So Cesar, please take it away.
Yeah, thank you very much, Dwayne. Also, thank you for the invitation to participate in this seminar. And also, thank you all of you for listening. I don't know if I can share my screen with you.
Yep. There we go. You can do it now, I think.
Yep. Let's see. I think so, yes. So can you see my screen now?
Yep, we can see it. So if you just want to put it in slide mode, we're good to go.
Yep. Great. So the idea behind this this seminar, it is to present some basics on statistical archaeoastronomy. I don't like very much this word of or this sentence of statistical archaeoastronomy because it brings probably Dwayne has already told you about ancient archaeoastronomy, where there was this debate between the green and the brown archaeoastronomies, one based on mostly doing statistics to try to get the data telling you something about the ancient people who built particular structures, mainly in Europe, and brown archaeoastronomy that it was mainly based on anthropological data and try to understand or to comprehend the reasons behind some actions or some notices that the anthropologists or other sources told us about people in the past. I think now this is more or less superseded. We have overcome these two poles. We are somewhere in the middle, but still it is interesting and I think it is useful, of course, and needed to talk about statistics in archaeoastronomy because it is still very much in use everywhere. In this, say, a bit more than an hour, and I will try to go from the basics, as the title says, to intentionality. Why intentionality? Because one of the main problems that we face when we have data on archaeoastronomy is trying to know or to be as much certain as we can that what we are dealing with is really something that has to do with, say, the sky, the sun, the moon, or the stars. And we will try to see how can we tackle this problem based on some statistical tools and probabilistic tools. When it comes to statistics, I always like to start with this sentence from the sign of 4, where Sherlock Holmes tells that while the individual man is an insoluble puzzle, in the aggregate he becomes a mathematical certainty. You can, for example, never foretell where anyone will do, but you can say with precision what an average number will be up to. Individuals vary, but percentage remain constant. So say the statistician. And even if this was written more than 1 century ago, it is still used today. The statements that they are behind these sentences, they are still used today, even when we see the polls for the elections or we see somebody trying to sell you something in the supermarket. They are based on statistics. But of course, we always have to be very careful and treat the data fairly, as we will see, and I will repeat this several times throughout these few minutes. Because if you torture numbers, they will always confess to anything. I mean, you can always try to tell the numbers, okay, you have to do this. And of course, if you tell them, there is a great chance that they will do. In any case, the idea behind this lecture is going from the very basics. I asked Duane, and he told me, don't expect that they are all of them familiar with statistics. So we'll go from very basic, trying to build up to something a bit more complex. I won't go into very technical details, only for a couple of things that I think they are meant to be explained in a bit more of detail. Um, if there is any question, any doubt, any comment that you want to do, just tell me. I mean, as you can see, I'm just sharing my screen. I don't have here the screen with all of you. So if there is any question, just open your mic and tell me, and I will stop and try to explain. Otherwise, I will continue talking. There are a couple of places where I set up a kind of stop between themes, and I will ask you if you have any questions or not. And there are a lot of practical also applications of what I'm going to try to explain. Okay. So in statistics, statistic is the science or the mathematics of big numbers. So to say, when we deal with big numbers, we want to know, as Serglog was saying, what is the regularities behind these big numbers. And this is what all this is about. When we try to, for example, study the orientation of megalithic monuments in the north of Spain, where we have thousands of monuments. Of course, if I have one measurement and it is pointing, for example, precisely to the rising sun of the spring equinox, I want to know if this is something odd or is something common. I mean, in these thousands of monuments, this is the common trend, or is it just by chance that this came out in this way? And to do this, I need these statistics. There are differences between types of statistics. Here include descriptive statistics, where we will see in a moment that it is only telling us how these big numbers are distributed in the different possibilities that they may have. Then we have the idea that these big numbers, when they come from, say, particular outcomes, there might be something behind that explains why they behave this way. And this is probably the way to try to understand a little bit more about the data is trying to compare this data with something else. And we will see this also in finally. And the final thing is trying to test some of our hypotheses. For example, I just made one on the orientation of megalithic monuments, which is okay, they are facing the sunrise at a given moment of the year. So this is a hypothesis that I would like to test. There are different kinds of tests, and I will show you a couple of them, and tell you how we can deal with this. So in this sense, we are coming from our measurements, trying to gather as much data or as precise data as we can to gain information, and from this information, trying to disentangle or scratch some of the knowledge that was behind these orientations. So our data, as I described just now, is the result of our observations. When we go out in the field and make um, research, for example, on the possible alignments that one can see from a panel of rock art, and we discuss, okay, this peak, this mountain over there, it might be important, and we do a measurement in that direction. This is our data. This direction, this measurement of the orientation in this case, for example, and they can be qualitative. For example, this panel is high up or high down in the ground. This is a sort of data that is telling us something qualitative, or it can be quantitative. I mean, we can express this in a number. So these are called the variables that we are going to work with. They are the characteristics of our observations. How can we describe them? We can describe them as discrete. For example, they can be either one thing or another, or they can be several things, but in a range. Or they can be in a continuum. For example, the orientation that we measure that goes from 0 to 360 degrees in a continuous interval. So as you can see, the way they are, the way we have these different variables, these different characteristics, the type of statistic that we are going to do is slightly different. Not in the sense that how we are going to deal uh, initially with the data, but how we are going to deal with the data once I want to understand how this data is behaving. A key concept in statistics is this one, sample. First, we need to differentiate between a population, which is the collection of all possible observables that we want to understand. Imagine that that I want to measure the orientation of all Roman temples in the ancient Roman realm. There might be thousands of them. Possibly a large number has been lost due to different reasons, especially due to the large span of time that has elapsed. And so we need to work with a small part of this population. Um, we consider just a fraction of this whole population, and this is our sample. For example, imagine that we take a sample on these Roman temples. There is some the temples from as many temples as I can measure from the Iberian Peninsula, from the ancient Hispania. Then this is my sample, and the whole idea is trying to from this sample and applying the rules of statistics, try to interpret how the population, the parent population, was behaving. There are a couple of assumptions in the way, of course. I mean, but we can try to understand the whole population with a certain degree of uncertainty, or uh, but we can manage and we can grasp and try to make this uncertainty as small as possible, to be as certain as we can on our conclusions for the parent population based on this sample that we have worked with. So coming to this would be the definitions, the basic definitions that we need from now. Data acquisition, as I understand, you already know how to archaeoastronomy used to work. If we are on the field and we want to measure, for example, the orientation of this building, say this temple or a tomb or something similar, and we decide that the important direction is from the inside out, then this direction, there is in this line with respect to north, is going to give us the azimuth. This is the direction, one of the orientation that we want to measure, but we must always take it into account the altitude of the horizon that we have in front. This is an angle as well. It's not the altitude, so to say, the meters above sea level of this mountain, but the angle that we can see from this position that this mountain is subtending. Of course, here the path of this star is as seen from the northern skies. From the southern, you would see it rising on the other direction. But in any case, with these two magnitudes, the azimuth and the altitude of the horizon, plus the location of this monument, the latitude, we can try to see, to verify if there is any star, sun, the moon that is coincident with this rising position in this direction. This is the basics. So the basics. So with this simple formula, where we have the altitude of the horizon, the latitude, the location, and the azimuth, we can get the declination. I'm not going to get into the details because I expect that you already know about this. How can we grasp, how can we obtain this delta, this declination? There are a couple of online tools if you don't have the software capabilities or whatever, but of course it's not very difficult to include this in a pocket calculator and obtain delta by your own. There are a number of other issues that they might help you to consider, like the atmosphere and so on. And for this, I would like to recommend these two online calculators for the declination. And then we have our measurement. Imagine that we only have one measurement, as I said at the beginning, and you want to understand if this measurement is relevant, is significant. This was already a challenge many years ago, when people were trying to understand if unique cases like Stonehenge or Newgrange, they were indeed relevant. Relevant in the sense that, okay, they incorporate orientations, say to solstitials in these cases, in these two cases, where you want to know if the orientation is relevant and is not due to mere chance that you have this. Well, there is a formula, an ugly formula like this one is based in the binomial formulation to calculate the probability of chance alignment. Comes like this, where I will explain in a moment what all these P's and N's and R's mean, but we can calculate the probability. And this probability, the smaller it gets, the less likely it is that it is due to chance. So the whole idea is trying to measure our to gather our data with as much precision as we can to a given degree of uncertainty, and trying to calculate these chance alignments. Of course, in any case, and as I said at the beginning, we cannot rely only on this probability of chance alignment. Even if the probability of chance alignment is very small, it can be out of chance. So we need more data. We always need to be aware that we need more contextual information, either from archaeological remains that they were dug by archaeologists within these structures like Stonehenge, Newgrange, or whatever, uh, and data from anthropology and ethnography if they are available. I always like to say that if I want to understand what the shape, I don't know if you can see, the shape of my mobile is, if I'm only looking on one point of view, from one point of view, I'm not going to understand if the depth of this phone. I need more points of view to understand this. So if I only relying on the information that Archaeoastronomy is providing, I'm not going to understand the whole picture. I need more data. So I need this context. So let's see how this formula works with an example. Uh, this image, this composite image here, is an image from my hometown, Santiago, in the northwest of Spain. This is what I can see from in front of my house. You can see that there is this horizon here where this is facing sunrise, different moments along the year. This is the cathedral, where the end of the pilgrimage route is bringing you to this cathedral where supposedly they lay the remains of Saint James. So it's the Cathedral of St. James, right? But there are other interesting things. And while I came to live in this house, I realized by chance one morning close to Christmas that the sun used to rise right behind the central dome of the cathedral as seen from my house. I said, okay, this is fair enough. It's nice. Um, but few years later, I also realized that this other church that you can see on the left, which is St. Martin, you could see also the sun rising behind the church at the 11th of November. And this is something funny because the 11th of November is the day of St. Martin. I said, interesting. And this tower that you can see on the left edge of the image is the tower of St. Francis. And I also realized that at the beginning of October, the sun rose also behind St. Francis. And St. Francis is celebrated also at the beginning of October. So I said, okay, this is starting to become a little bit odd. So I wanted to calculate how probable it was that in three directions that I have here from in front of my house, I could see the three directions are related because the solstice is also related. The date of the solstice is also related to St. James. How it comes that from this single point I could see the sunrise at three moments that they are linked to the three churches. Of course, these are not the only churches that I can see from my house. There is a fourth one to the left of the image, which is St. Susan. I think I couldn't find any relation in that case. So in three cases out of four, I could see a possible relation with the dates of the celebration of the saints from my house. So I wanted to calculate what are the probabilities, what are the odds of having this out of chance. So this formula is giving me the probability of chance alignment. In short, is the probability of hitting R targets in N shots, where this capital P is this probability of chance alignment. The small p is the portion of the horizon covered by the targets, or the uncertainty in our measurements. So to say, is the probability of each of one of these of hitting one of these targets. And to this, we must bear in mind that, okay, these are not small parts of the horizon. And this is the key part in this calculation. For example, the cathedral subtends almost 10 degrees in the horizon, as seen from my house. St. Martin, nearly 15. St. Francis, that I cannot see completely in this image, another 10 degrees. And then St. Susan, another 3 degrees, which is a bit farther away, and I can only see a part of the church. So there is a large portion of this horizon that I can see that it is covered by these different churches. And this is the probability that I need to include in here. Of course, I have to be careful. I could say, okay, compared to the whole horizon, this is only like, say, 38 degrees. So it will be like 10% of the whole horizon, 360. But I'm not considering anything that is beyond the area where I can see the sun rising. And the arc of the horizon where the sun is rising from Santiago subtends only 66 degrees. So in this case, this portion of the horizon covered by targets is nearly 58%. And this is, as I said, a key part in this calculation. As I say, we need to be fair to the data and do this before and estimate all this before we know the final probability. Otherwise, we are always going to say, okay, no, I'm going to torture the numbers, as I said at the beginning, so that this P is much smaller and the probability of chance alignment is very small. How many possibilities we have? We have four. We have 4 hits possible at the Cathedral, St. Francis, St. Martin, and St. Susan, and 3 hits where we have these dates that are relevant for the 3 churches I explained at the beginning. So including all these in this formula, then I come out at the end with a probability of 0.74, which is a large probability. It's a very high probability of having this number of this result purely out of chance. Imagine that tossing a coin is giving you 0.5 of a probability. So it is almost certain that I'm going to have this. I mean, and the whole idea is that the angle that is obtained by each of these churches is very wide. So we need to do this very carefully when we try to calculate these probabilities, and always be, as I said, fair to the data. Okay. If you remember, I said here that also we can, if we imagine that the only thing that we have is a single position on the horizon, that we want to know if this is related to our measurements. In any case, we need always to take into account how precise or imprecise, how accurate or inaccurate are our measurements. With a single measurement, we cannot be sure if we are in a case like this, where we have almost hit the target, but we are out and we are imprecise, or we have a bias, a systematic bias in our measurements, that it might be corrected, but we need to correct it, and we need to know. So we need to verify first if our measuring device, for example, is biased, or if it is precise or accurate. So this would be the ideal circumstance. But in any case, we need to know how our dispersion, how dispersed our measurements are. And this is giving us a sense not only on the accuracy of our measuring device, but also on the precision of our measurements. So let us, for a moment, concentrate on some measurements, like we take it with a compass, for example, of this building that is facing west. The north is up, and we are facing west in this direction, but we cannot measure this from the inside for whatever reason. So we do it from the sides, from the points A, B, C, and D. And we take a number of measurements from A, number from B, from C, and from D. So at the end, we have a number of measurements that we want to put all of them together. We have 14 measurements. We say, okay, let us put all of them facing the same direction as A. So these ones, I will just subtract 180, put all of them together, and calculate the mean. Don't worry, I will explain now how to calculate the mean in a second, but this is just giving you the average of all these numbers, okay? With a dispersion between them of 0.4 degrees. Okay, fair enough. And we measure the altitude of the horizon in this direction, and it's 4 degrees. Okay, fine. Then we have our measurements here. We verify that the magnetic declination of the site is 3 degrees west. So we need to subtract 3 degrees to A, and our corrected azimuth is this one at the end. So, but remember, this is A, and our direction is this one. So we need to add 270. So our final direction in this for this building would be this one. We implement all this in this formula, and we come out with this declination, 7.4 degrees. That can be equated, for example, imagine that this is something that we know from other sources that could be related to sunset somehow, and we want to know for which dates this would be relevant. And we can calculate that this is for 9th of April, the 3rd of September. Fine, fair enough. Later on, we can try to verify if this is relevant or not for the people who build this structure. But in any case, we always need to realize that these measurements and this data that we have here include errors. Anything that we do will have an error, and we need to acknowledge that this error is going to affect the certainty on, for example, these dates. For example, our measuring device has an uncertainty of, say, 1/4 of a degree. But we have seen that our deviation, coming back here, let me see, here, our deviation or standard deviation, I mean, our mean is somewhere here, but we have that large number of our measurements are not hitting the target, but are spread around it. This is the meaning of this standard deviation, okay? Is 0.4. Besides this, we need to evaluate the remains. Imagine that we have measured this and, okay, the walls are a little bit bent, or it was somehow squeezed, and there is an uncertainty of 10 centimeters in a building of 10 meters. So this would equate to something like 1/2 degree. So we need to include all these in our uncertainty in the azimuth. In the altitude, we may have that it is 0.5, and we need to calculate the uncertainty in our declination, which would translate in something nearly 1 degree of uncertainty in that 7 degrees. And this will, depending on the time of the year, equate as few days or several days in the uncertainty in the dates that we had for this structure. How can we be a little bit more certain that this thing that we have measured, for example, with this monument that is facing to the equinox that I was saying at the beginning, is really facing to the equinox? We're measuring a lot of them. These are the statistical studies that allow us to verify if there's a pattern or there is an anomalous orientation within this pattern. For example, imagine this tomb in Petra. This is the tomb of Sextus Florentinus, which is the tomb of the first Roman governor after the annexation of Nabatea, Arabia Petra, to the Roman Empire. He wanted to be buried in Petra, so he built this tomb in the way the Nabateans used to make their tombs. But curiously enough, its orientation is completely at odds with the orientations of the rest of Nabatean tombs. While all of them, all the Nabatean tombs are facing, as we will see in a while, within the solar range, this one is facing north. Why is this? We can speculate and we have some information about that, but we can verify precisely, measuring many other tombs, that this is an outlier, if you want, or something strange and something anomalous that is happening with this tomb. Be aware, there is no noise in the sense that we have noise in physics, for example. There is no sources of natural noise. In the meaning that anybody who built something had a reason to build it that way. We may not know why they did it that way. We may not know the reason, but there is a reason behind that. I mean, we are going to find patterns, and we are going to find some patterns that they seem less pronounced than others. So these patterns that are less pronounced are not noise. It's simply that few people built it that way, that in the other way. In the absence of all the data, we need, in several cases, to rely on this statistical treatment of the data. This may allow us to measure the significance, the intentionality. And this was something discussed many times in the past decades within cultural astronomy. We are only saying, okay, there was an intentionality here, because if I measure, for example, 1,000 monuments, as I say, megalithic monuments, and I see that the largest concentration is facing, in this case, winter solstice, there is an intentionality behind that. But we don't know the meaning of that. We don't know the intent behind that. To grasp this meaning, this intentionality, is why we say that we need to consider the context. And finally, this statistical treatment may allow us to do some modeling to understand what is behind this. So let me go now fast on this part. I don't know if there are any comments or questions up to now. No? Okay. Let's go to the details on descriptive statistics. First, we may have tables. Here, for example, we have a table with data from Roman temples, from France and from Gaul. And you can see that we have in the rows, we have the observations made. For example, here in chart, we have the tempo, the latitude, the azimuth. These are all the observations that we have done. And those that we can derive. For example, here, that we can see the dates that are connected to this declination, right? In each of the columns, we have a variable. We have the azimuth, the altitude of the horizon, the declination. And each cell is giving us a datum. With this, we can build frequency tables. For example, we can say, okay, what is the frequency of having this number here? Well, there is 1, 23, 26, or whatever. I can build relative frequencies. For example, this is the sum of all of them. So if I divide 1 by 189, then I will have the relative frequency of 0.005 or whatever. And with this, I can build later on some graphs that they may tell us something on our data. And these are the representations. As I said, we have nominal and ordinal data. For example, we can build a bar chart. All of you have seen these kind of representations or pie charts because we are all used to see all these, for example, in the news, where they give us the statistics of people that is buying a given item or other things, goods or whatever, right? So these are the bar chart and pie chart that is giving us some visual characterization of our data. And this is very useful to know how the, for example, in our case, the orientation is behaving. For example, in this case, one of the most commonly used diagrams for the orientation of monuments, for example, here again with the Roman temples, is the Hoskin or orientation diagram. This is just the representation of the horizon. You can see here, seen is this circle, where we have included these directions on the outskirts of the circle, indicating the cardinal directions, and the rising of the sun or winter solstice in the northern hemisphere, sunset as well. We can include also the moon if this might be relevant in some cases, and we can see in the inside the directions of the temples, indicating, for example, with different lines, different types of temples if we want. If we have continuum data, we can build histograms where we only include here, for example, a number, our magnitude, say, for example, distance from water source in this case, and the frequency, how many of the items that we are considering are, in this case, at a given distance from us. And we can see that this behaves in a certain way. With this, we can build our frequency table, and when we say, okay, how many are in this interval of the data, and we can see that this is building up to a given point where we can see that, okay, this is almost flat in this direction. These are called the ogive of the frequency, the accumulated relative frequency in this case. Okay, so it goes from 0 to 1, and we can see how fast this grows, or and try to identify in which distance this is almost flat, for example, in this case. With two variables or three, we could build also 3D representations. We can do scatter plots. For example, in this case, distance and angle, and we can see how when distance grow, the angle becomes much smaller, for example, in this case. And we can start to understand that there might be a correlation here, a relation at least, between the angle and the distance. An interesting representation that has been very much used in the last years in archaeoastronomy is instead of using the histogram, is trying to use a kernel density plot to build a curvigram. What is this? Imagine that you have these 5, 6 points here. One data is almost at 6 point something, one is 5. Here you have another one at say 2 or 1 point something, and a couple of them are in negative positions. Then you may have that, okay, in this box I have one, in this box I have two, in this one I have one, here I don't have any, one and one. And you can build this histogram. But as you can see here, for example, our data is very close to these ones. Is there a way to incorporating, for example, our uncertainty in the measurements that we have seen that this may have an error to this shape of the histogram? Well, this is done with the kernel density. This is like this, where you have for each of the data, you include a curve. Instead of a box like here, we include a curve like this. And you just simply add these curves, and at the end you end up with this soft line here that is something similar to this, but is giving you more of a sense of how the data is distributed. There are different kernels. These curves are, these small curves are called the kernels. We will see in a moment the Gaussian. The top hat would be simply a representation of these ones, and there are other possibilities as well. So the final result of our curve will vary from here to here and from something slightly different if we use different kernels. We can go from very coarse representations of our orientation from south, winter solstice, equinox, summer solstice, north, to something more nuanced, like this one, for example, where we can see different directions. In this case, the dotted lines, for example, indicate the solar range in a given position for a number of monuments, and we can see that there is a concentration inside the solar range with some characteristics that might be interesting for us. Distributions, the distribution of data, we can understand this trying to incorporate some numbers that they may describe these distributions. Some of them tell us something on the central tendency, where most of the data is located. For example, imagine that we have this data, this number of data that we have collected, say, for example, orientations or whatever. The first number that is interesting is the mode, which is the most repeated value. In this case, the number 9 is repeated 4 times, so this is our mode in here. The median is the value that divides our sample into halves. We order our data from low to highest, and then the one that is in the middle would give us the median, in this case 7. And the mean that we have seen a while ago, it is simply the arithmetic mean. We sum all the numbers, divide by the number of elements that we have here, and then we have our arithmetic mean. In this case, slightly more than 7. So it's slightly different than the median. So you can see that in general, the mode, the median, and the mean are not going to be the same number. There are certain special cases that we will see that where these are always the same, but in most cases, we are going to see that this doesn't need to be the case. There are also measurements on the dispersion that we have seen. Our data can also be dispersed. The first one is the range, is the difference between the maximum and the minimum values of our sample. In this case, 3 and 13. So our range is of 10 whatever, 10 degrees, 10 kilos, 10 degrees of temperature, whatever. Then we can separate again our data, in this case in 4 intervals, and these are going to give us the quartiles, 35, 50, 75. Q2 is the median, so we have these quartiles. Again, measurements on the dispersion of our data is given by these two weird expressions. One is the variance and the other is the standard deviation, which is the square root of the variance. And you can see that, for example, in our case, this is 2.8 degrees And this indicate how far from the mean is a part of our data. We can plot this here, and you can see this is our data, and you can see that this is the mean, and these two lines indicate plus and minus, the mean plus and minus this standard deviation. And you can see that a large fraction of our data is within these two lines. So this is what the standard deviation is telling us. And this may be connected to an estimate of our errors. There are several estimates. I won't go into the details here because it could deal. It could take a whole lecture on errors only. So these numbers are going to give us the sense, the flavor of how our distribution is. These are the numbers that we have measured. This is the mean. As we have seen, the median is also very close to it, but this is the mode, which is 9, if you remember. And these two are the range from 3 to 13, and these two are the standard deviation. So as you can see, different numbers that is going to give us this sense of how these are behaving. Remember, this is just a representation. In order to say something, we need to take the numbers, and these are the numbers: the mean, the mode, the median. There are other numbers, but these are the basic ones. How can we obtain all these? Of course, if you are fluent with Excel, you can do it with Excel. There are several spreadsheets where you can do all these, and some of them are available online or on request. If you want, you can drop me an email. I can send you some of these for you to work with. If you are fluent in R, there is Skyscape R made by Fabio Silva and collaborators, where you have a large number of well, there's a whole library basically devoted to the implementation of statistical analysis and treatment of the data, where you can at the end come out with plots like this and statistics on these numbers. We in our group tend to use either IDL, which is very commonly used among astronomers, or Python, also very commonly used. In the few months in the future, we pretend to open these to anybody. At the moment, you can drop us a line, and we will send you the files on request. But from the moment in a few months, sorry, we will put all these on a GitHub, so anybody could also download these from the web. Finally, trying to come to the final part of the lecture. After we will try to come to some examples, practical examples of how we have dealt with items like this. Let's go to statistical inference. We have seen how data is distributed. The most common way that we see most of the data is distributed is a normal distribution. It is called this way precisely because of that. It was described by Gauss, the German mathematician, several centuries ago. And this is why it is also called a Gaussian. Okay. Yes. I will come to this in a second, Amanda, if you allow me. In any case, the short question is STDEF, I think it is called. STDEF in Excel is probably one of the best. The best solution is always to download. There is a whole set of data, a set of tools that they are incorporated in a module that is statistical tools for Excel. So you need to download these to have the whole set of statistics in Excel. In any case, this distribution, the Gaussian, um, it is the one that it is most common that we see in nature in many cases, and also it is interesting that it is the one that has a number of mathematical characteristics that allow us to use it, even in the case where we don't know if our distribution is normal or not, and we will see this in a moment. So the idea is trying to understand the population from, as I said at the beginning, from our sample. And to do this, we need to make some assumptions on how this data is behaving. The most common distribution of data, as I said, is the normal or Gaussian, and has this appearance. Here you see, for example, the data is given here in a particular way of numbering. This just center in the mean, which is in here. Sometimes is given as x bar, or sometimes is given as mu. There is a reason why these two things might be used differently, but I won't come into the details here. But you can see that most of the data is close to the mean, while as we go away from the mean, the things tends to be less and less with this distance in here. And the shape is given by this formula, where sigma is the standard deviation. Here you have the mean and the standard deviation here. And this is the most, as I said, the most common distribution in nature, as we have seen. There are several theorems that tell us that if our sample is large enough, we can use the normal distribution and the normal characteristics to try to understand how this distribution is behaving. And it can be used as a proxy, as I said, for other distributions. Interesting thing is that within this one sigma, we have 66% of our data is going to be inside of this envelope here. If we come to the 2 sigma, which is this one here, 95%, sorry, of our values are going to be in this area. And if we come to the 3 sigma, or a little bit less, it is going to be 99% of our values. Okay, so this is giving us a handle on how the data is going to be distributed. How do we work then? Then we assume a hypothesis. We need to there are several different things within statistical inference. There are hypothesis testing, test of significance, exploratory analysis. We will go a little bit in the first two here. What is a hypothesis? It's something that some assumption that can be quantifiable that we do regarding the data. For example, we assume that the data is distributed as a Gaussian, or that is distributed as the way, as we will see in a moment, that the sun rises along the horizon, or particular dates. This is our hypothesis. And this is the hypothesis we want to test. The hypotheses, they are theories or are based on them, but not all theories provide hypotheses that can be tested in this way. So this should be taken into account while using these tools. How it works? We assume that our data follows a given hypothesis, like we call it H0. We build an alternative hypothesis. Basically, it's not H0. This is our H1. the alternative hypothesis. And we try to show with a degree of certainty that this H0 is not true. And this is, if we succeed, we say that our data doesn't follow the null hypothesis with a given level of confidence. And this is what we used to call the p-value. The p-value is the value of this probability of chance, for example, that we saw before. And I say caution. Okay. For more than 100 years, we have been using in statistics certain levels of confidence, like, for example, 95%, 99%. So to say, if the p-value is 0.05 or 0.001 or something like this, we say, okay, beyond this percentage, we are certain that the data doesn't follow this null hypothesis. This has been taken as okay. Then we are sure that the data is following this alternative hypothesis, and this is a problem. With this, we are only saying that given these tests, I'm up to this level of confidence, sure that the hypothesis H0 is not followed, but it doesn't mean that it's not followed at all. Okay, it gives you a confidence, but it doesn't tell you that this is completely true. And this is something that we need to be cautious about. Usually this means that the alternative is supported. But what we have shown, as I said, is that our data doesn't follow the null hypothesis to a given level of confidence. For example, imagine that we have these two types of temples. The ones on the top are Greek-style temples in the southern part of Turkey, in Lycia, while the one on the bottom are Greek-style temples in Cyrenaica, in the north of Africa. Different regions, similar structures, possible links, cultural links. We measure the orientations, and then we come to these distributions of our data. And we see that some similarities, but we want to see if they are similar or not. So our H0 is that they are similar, H1 is that they are not. We built our test, in this case, the Kolmogorov-Smirnov test. I won't go into the details here, but it's a way of comparing distributions of data to tell you they are coming from the same parent distribution. And we say at the beginning, if p is less than 0.05, we rule out H0. And we do the calculations. We find that our probability is not less than 0.05, so we cannot rule out H0, that they come from the same parent population. Look, this doesn't mean that they come from the same population. We need something extra to say, okay, they are coming from the same parent population. But at least the statistical treatment is still telling you that something on this data. They are possibly, you cannot rule out that they are coming from the same population. We can do this with these curvigrams, and the idea is trying to test the significance. You have seen in here this data. How much more significant is this peak here, for example, than these ones on the sides? Is this concentration the only one that I should consider, or should I consider all of them? To do this, we need to compare our data with something. And to do this, for example, I could compare my data, in this case, the black line with the blue line. This is the line that I would expect if I would distribute my data evenly on the horizon and then transfer this into declination. This is what I expect. You see, I expect that I would have a minimum in declination 0 and a maximum going up north and south. This is due to the inclination of the declination lines, either on the northern or southern horizon. You will see that these lines are going to be tilted, and when you go to the horizon line, you will have a larger probability, a larger density of the declination lines in north and south, and this is why I have these maxima, so to say, in north and south, and a minimum in east and west. So I could compare these with my data and try to understand how they behave. But still, this doesn't tell me, for example, if this concentration towards south is significant or not. To do this, I would need to do something else. I will show you in a couple of minutes 2 videos. These 2 videos is telling us what the sun and the moon do in the horizon, in the case of the sun along the year, in the case of the moon in nearly 19 years. Let's start with the sun, and you will see that the sun starts in this horizon in here. This is December solstice, and you see that it bounces here, somewhere here. This is June solstice. Let's do it again. You can see that there are these 2 points. These are the 2 solstices. That is where the sun stops and goes back to the initial position. And there are some position around here where it moves very, very fast. Okay, this is going to tell us something on the distribution of orientations of if I would orient a structure to any given day along the year. Now for the moon does something similar. I would focus on the full moon starting here, and along the months it bounces back and forth. You've seen that the initial position now is changed. The extreme is going inside. These are the different standstills. And you can see that after 9 years, it bounced back to the extremist position. After a little bit more than 18 years, it gets back to the major lunar standstill. And if we build the different distributions that I can consider, for example, for a homogeneous distribution on the horizon, for a homogeneous distribution along the sunrise or along moonrises, you can see that the distributions are going to be different. Not widely different, but they are going to be different. The ranges in this case are completely different from these ones. And you can see that the prominence of the maxima in the case of the sun is different from the homogeneous one. And in the case of the lunar distribution is somewhat different. For reference, the solid lines are the solar range limits. The dashed lines are the lunar limits, where here, for example, is the minor lunar standstill. Here is the major lunar standstill. Then how this compares to my data. For example, in this case, I have a number of data in cyan, in light blue here, that is compared to the homogeneous distribution here. You can see that the homogeneous distribution is given by this white line here. My data is in blue. And what I've done is trying to understand how significant are these concentrations compared to the distribution of the homogeneous data. As I said earlier, I want to see if I can disprove the null hypothesis, that they are, in this case, oriented randomly. So then what I do is try to see if I can get this distribution from random distributions of this homogeneous one. These are the black lines here, that they appear so puffy and so these are thousands of distributions that they are taking random numbers of the same, random samples of the same size as the blue data from this white distribution, you see? And with this, for example, this white dotted line is giving me the mean, this data plus one standard deviation obtained from this random sample. Then I can build something called the z-score, which is comparing my data, the blue, with the white line here, divided by this distribution, this dispersion of my mean data, my hypothetical, my theoretical distribution here. And then I can build something like this, where anything that I set at a limit saying, okay, anything that is 3 times or 2 times above this line, I will consider this significant. And then I could say, okay, there are concentrations on winter and summer solstice and perhaps the equinoxes. And then I can go to the data, to the other type of data, archaeological, ethnohistorical, anthropological, and try to understand all these. So with this, I would say this is the whole lecture. It was a little bit above 1 hour. If you have questions, I think this is the moment, because I'm sure you will be full of doubts, of comments, of things that you don't understand. But also I have some examples for you to show some of these applied to the real world and things that we have tried to understand. There is a comment in the chat by Martin that there is a lot of criticism of null hypothesis testing in science reform movement for precisely those reasons. Lack of support for H0 cannot be itself the support of any given alternative. We need more information for that. Exactly. This is one of the things that I wanted to imply with my comments on the p-value. There is a lot of discussion, and people are now more into, okay, saying it's better not to tell this is beyond the value, this one, but providing the p-value for each of the data that you have. This is why things like this, things like this are useful. Okay, you can set up here a limit to guide your eyes, but you can see how different the distributions are in these concentrations, compare one to the other. And as I said at the beginning, these data are all of them significant, in the sense that even if they are not statistically significant, these orientations, they had a reason to be there. Okay. So if you have any other questions or comments, please go ahead.
Well, thanks, Cesar. So I think in that previous one, what we might say is there's certainly some preferred orientations that tend to include the solstices and equinoxes, but there's other ones as well. So yes, it's curious how we draw meaning out of these kinds of analyses, but that's really great. Do you have any other questions from anybody?
No, did Amanda have one back in the chat?
Amanda did have one saying that in Excel, there are several commands that can calculate standard deviation. Which one do you recommend we use? Nothing.
Yeah, I mentioned before there was this package that can be used with Excel that you need to download, which is statistics for Excel, and stdef there is one of these commands. Yeah, so yeah, you can use this. In any case, I mean, Excel is a very useful tool, and it can be used, and it's widely used everywhere. But there are other options if you need them, like for example in R, in IDL, in Python, in many other I don't know, in C, whatever. There are options that you can use as well if you are fluent in that. I mean, all these you need to remember that as in any other software, it takes time to get fluent in any of these tools. The good thing, for example, with R or what we are building now for Python is that they have Skyscape R and our library in Python. They will have very detailed explanations on how to do things and why these things are done in this way, so that you can understand how they are built, what they do, so that you don't use them as a black box, basically. That is something that we usually do with many of our software, that we input a number and we just interested in the outcome, and we don't know what is happening in between. And we need to at least get a sense on what is going on in between, so that we know that that number that is coming out has a sense on its own. Okay.
Jamie?
Thanks, Cesar. That was fantastic. I was just wondering if you could speak a bit to recording standards and geographical disbursement. So what would you consider to be the minimum number of sites for statistical overview, and positionality in the landscape? How far can you go trying to gather that?
Okay. In my experience, well, so to say, this is going to, the way of answer I'm going to give you is very typical of the region in Spain where I'm living now, which is telling you yes and no at the same time. So it depends a lot on the kind of data that you are going to work with. For example, 4 cases, it could be enough if you have some ethnohistorical or anthropological data that is backing up that all these 4 data are related. Okay, so you need context anywhere. If you don't have this data, I would say that you need at least a sample of larger than 30. In many occasions, this is going to be challenging. For example, imagine that you go to a small island in the Channel Islands where you have megalithic monuments. The island is very small, and try to see if there are 30 megalithic monuments in this island. Probably there were not in at any time in history. But if you want to plot any of these figures and graphs and try to understand if they are all of them related, and so this would be my advice. Go to at least on the order of 30 up and above. The higher the number, the more confident you are going to be on the concentrations that you are going to get. For example, I've seen that one of the last lectures is by Juan Antonio Belmonte, who is going to talk on Egyptian archaeoastronomy. He will show a large number of temples that he was able to measure along the Nile and away from the Nile. And you will see how the statistics varied along the different seasons of field campaign while the number was growing. There were some characteristics that they were already there from the beginning, but others that they only appeared when the whole sample was there. Okay, so this is something interesting and challenging at the same time. This is something that you tend to learn more along the way while you are doing the field work. I don't know if I answered more or less your question.
Pretty much. Thank you.
Basically in 30, yeah. Cesar, do you utilize or do much work with Monte Carlo statistics or Monte Carlo simulations? You want to speak a little bit about that?
In fact, let me see. I'm still sharing my screen, right?
Yes.
Okay. Let's go back here. This is basically a Monte Carlo simulation, right? So what you do here is taking sample like this, and you draw as many different random samples from here with the same number of individuals as in the observations, trying to build these other envelopes here to see if these concentrations are consistent with being just randomly chosen from this population or not. And this is the way we have come out with this distribution here. So yes, we do it in this way.
Excellent. Thanks so much.
So I don't know if there was any other question. If not, I would like to very briefly go at least into a couple of the examples I had here for you. The first one was with megaliths on the recumbent stone circles from the UK, from Scotland. Many of you already may know that they have this appearance. They are stone circles where you have one of the stones is recumbent, is lying, and is flanked by these two standing stones. And they are very typical from the northeast of Scotland, close to Aberdeen, where there were nearly 100 of them, but only 50 of them were in conditions to be measured by Clive Ruggles in the 70s. And he was able to measure the orientation because the position of the recumbent stone was basically quite systematic in all cases. You can see that it's always in the southwest. And if you are placed up on the central part, you can define this direction from the center to the middle point of the stone. There are other ways, of course, of taking the orientation, but this is one of them. And at the end, when you transfer this into declination, you can see that the histogram or the curvigram of the declination is this one. The lines here, the yellow lines here are giving you the solar range. So you can see that most of the orientations are outside of this solar range. So there are a few of them that they are inside, but most of them are outside. While the red lines here are giving us the lunar streams, the lunar range. You can see that most of the orientations are simply connected to the southernmost position, in this case, the southernmost setting of the moon. So I could, again, try to compare with the sun and the moon, and you can see it doesn't follow the moon along the whole cycle, but it seems to follow something related to the moon, the setting of the moon at the end, not at the end, at the southern stream of this cycle. So we could try to imagine that, especially at these latitudes, this is high up in the north, the moon, this is the summer full moon, is setting and is almost rolling up on top of the recumbent stone or the mountain behind. In several cases, there is a mountain behind, which in Scotland is not that strange anyway. And you can try to build now an interpretation based on this. You have seen that a large number of monuments are connected in this way. So at the end, you can now start to build this interpretation on the data. So just to say that in this case, for example, the statistics are the ones that they are telling us that these orientations are relevant in this case. If I would have only one measurement, one case, okay, it would be interesting to see this connection with the moon, but to be a bit more certain, I need the sample as large as possible, as I said earlier. Another example, it could be the Nabatean temples. We have seen one before. We have been doing research in this area of the Middle East where Israel and Jordan and Saudi Arabia are located. This is where the Nabateans used to live at the turn of the era, so to say, a couple of centuries before and a couple of centuries after the Common Era. And they are mostly known by carving these facades in Petra, their capital. They had a number of divinities that they equated with different bodies in the sky, like the sun, the moon, Venus. I won't go into the details because I don't have time, but they tend to represent them uniconically, like stones like this. And the later representations, after in Roman times, they included these anthropomorphic figures. We have sources from Roman and Greek sources that is telling us that they perform some kind of rituals in the roof of their temples with that where they worship the sun and they burn incense and so on. And we have epigraphy from several sites where we have data on the calendar from these people. And we could see that not all inscriptions, they mention all months along the year, but there are some inscriptions that they are related mostly with some months. They are connected, for example, with the solstice, with the equinoxes, and perhaps also with the solstices as well. So the idea behind our research was trying to get a sample as large as possible on temples and cultic places in this area, trying to measure their orientation and see if their orientation equates somehow with this information. And it does. It comes to the result that when you compare the orientations, you can see that most of them, they are facing east in a broad sense, and perhaps the solstices, which is relevant in this case because you see that the information that we have from other sources is telling us that these moments were important for them, and they somehow fossilized this in the orientation of their cultic places as well. And to end, I have these measurements on churches as well. You may be aware that Christian churches, they need to be oriented. Even the word orientation is telling us something on the way we are facing. Orientation is telling us to face the Orient, the East, and this is the orientation that a church should have. The main part of the orientation is this one, which from the outside could be thought that it is the back of the church, but it's actually the front part. When you get inside, this is the part where the altar is located, and this is the way the priest and the people is facing to, and this part should be facing east. So we measured a large sample. In this case, as you can see, large for us is a number above 200 Romanesque churches along the way of St. James in this area, in different kingdoms, medieval kingdoms, and we could see how the orientation is related to what I would expect with a homogeneous distribution, as I said, solar one, a random sample from the solar one, centered to the east. I would expect something like this. In this case, east could be meant by the Easter. And you can see that, for example, here we need to take into account the differences in the calendar. We are using the Gregorian calendar today, but in the Middle Ages, they were using the Julian calendar, and this calendar shifts with time the positions of the orientations on a given date with that one on the Gregorian one that is following more or less that, for example, east should be here. And this is something that you can see the shift in these positions, for example, for the 21st of March. For 950 or for 1450, you can see that there is a shift, there is a displacement of this given the discrepancy between the Julian calendar and the tropical year. So with this, we went to our data, and in the 275 churches, we can see that all of them are facing the eastern horizon. These are the ranges of sunset and the sunrise between the solstices, and most of the churches are, well, considering the altitude of the horizon, even most of these ones are inside of this range. Only a few of them are facing north, and you can see that all of them are facing close to east. When we do the calculations with the declination, we compare with the homogeneous distribution and the solar one, we can see that our distribution of orientation is something else, something different. It is not a homogeneous one, is not following any day on the calendar, is something else. And this something else, when we come out and explore modelings, this is what I meant before by modeling, I could calculate when Easter is going to happen in a number of years. In this case, we did it for 200 years. That is when the Romanesque was the main style to build churches in this area. And we can see that the main concentration is very much related, in this case, to Easter, not to the east, but to when Easter Sunday is going to happen. And this appears to be differently in different kingdoms along the way. For example, in the kingdoms of Leon and Navarre, I see more concentrations towards east, while in Castile and Aragon, the concentrations towards Easter are more prominent than in the others. And I don't know if I have time to tell you the last example.
Yes, that's fine. Great.
Yeah, okay, great. The last example is trying to grasp a little bit more or torture the data a little bit more based on the orientation of megalithic monuments in this area in the Mediterranean. This was based mostly on data from Michael Hoskin, who was obtaining this data for the last decades of past century, say from the 80s and 90s. And he was able to gather almost 2,000 measurements of megalithic monuments in this area from several groups of monuments from both Portugal, Spain, the south of France, and the islands in the Mediterranean, different types of megalithic monuments. And you can see that most of them seem to be facing in a coherent way within the groups. I mean, they seem to be mostly related among them. And in many cases, you could see some more group or less group dispersed orientations. Like, for example, these ones compare to the ones in central Portugal or in the Pyrenees. You can see some differences. But in any case, the interesting thing here was that he was able to prove that each group had a coherent orientation, and this orientation was something meant and interesting to consider when studying these monuments. Most of the megalithic monuments in the Iberian Peninsula are facing within the solar range of sunrise here. As I said, these are nearly 2,000 monuments, and nearly 80% of them are in this range, which is slightly north of east and just up to the solar solstice sunrise, or even the moon, the southern extreme moon in the east. But one thing that we wanted to do, it was to compare all this data and see if we could find similarities among them. We could see some of them that they are close together, like Elvas and Alentejo, they are very close together. But we wanted to see where these similarities, up to where we could find these similarities, and if this was leading us to anywhere. So we were using another statistical tools that they are the multivariate analysis, where you can build these dendrograms out of them. Well, what you are doing here basically is that you have a number of data, a cloud of data like these ones on the right. You build groups based on a recipe where you say, okay, I will build these groups by nearest neighbor, for example, or by a centroid analysis or whatever. And then I build distances to the other groups. And with this, I built a tree of distances. A and C are close together between them. Then there is B, and then there is D. And with this, I can build these kind of dendrograms here, for example, for European languages. They were very useful and they have been used in many different areas, like biology as well, for example. And what did we use? We used the same things, the descriptive statistics that we were seeing earlier. We used the mean, the median, the standard deviation, the maximum and minimum, the range, and the maxima of the concentrations in these distributions. So we took these 7 numbers from each of these distributions. For each of the different groups, we extract these numbers, and then we build our matrix of data and employ this multivariate analysis to build the groups. And what did we find? It was that indeed there are families of orientations that they are grouping in a broad areas. Some of these are far away, like almost nearly 1,000 kilometers from top to down, and the similarities are striking. The similarities between different groups in different areas are telling us not that they are connected, in a sense that they were people traveling up and down. In some cases, there are some suspicions that this could be so, but more that they have the same or very similar orientation, that they were looking at very similar things possibly in the sky, and that the orientations there are very similar. And this is helping us now to try to see what these connections with the sky might be. For example, in this case, in the eastern part of the western part of the Iberian Peninsula, what we have is that the most of the orientations are connected possibly to a lunar, an Easter or equinoctial moon, either on Easter, either on autumn. We are still struggling trying to disentangle if it is possibly more in the autumn than in spring, that is connected to the orientation of these monuments. While in the Northwest, this would be much more connected to orientations clustered to the winter solstice. In other areas, we have other possibilities, but this is helping us to now build larger sample and be able to model how these would behave if they were following this or that target. So with this, I would like to end, and I think I'm open to your questions, your reactions, your comments.
Thanks, Cesar. I appreciate that. It was a fantastic overview. One thing that comes to my mind, you were talking before about the recumbent stones, and there were preferred alignments to the southwest which seem to be aligned to the southernmost position of the lunar maximum lunar standstill, or major lunar standstill. Now, one thing that I find curious is we did a survey of ceremonial sites in Southeast Australia several years ago, where they primarily consist of two circles, a larger circle and a smaller circle connected by a pathway. And this was one of those cases where we had a large number of sites that we could draw data from about their orientations, but we also had some ethnographic data. And one of the things that was really interesting about this is that if we were to look at translate the azimuth to a declination, we may have come up with something quite similar, that it may have been around these lunar standstills. However, what we found from the ethnographic information is that it was connected to the position of the Milky Way in the sky at that particular time of the year. At that time of the year, or at a particular time of the year, which is about now, August and September, that you would see the Milky Way from Australia perpendicular to the horizon. And this tied into the animal, the emu, the bird, whose eggs began hatching. They began fledging the young right around that time. And the ceremonial sites were about bringing the boys into manhood. So it was an initiation site for young men. So it was symbolic of the emus rearing the young, because the male emus, the ones who would sit on the nest and rear the young. So we had that information, and that tied into the ceremonial sites and their orientation. Now, the ceremonial sites were often described as relating to the emu and being sort of a physical reflection, that direct connection between land and sky. Now, if we didn't have that and we were looking at declinations, we would have come up with a completely different hypothesis, because the Milky Way isn't a declination. There's no declination for the Milky Way because it's huge, spread across the sky. It doesn't have the declination of a specific object. So that's just something I was just thinking as you were talking about that tied directly into work we were doing, but how our results changed quite radically when we had some idea about the ethnographic data points on that. Anyway, it's not a benefit or criticism. It's just something interesting that I realized you were speaking about that.
No, if I may, you're completely right. I mean, is what I said at the beginning, that you need more data to be able to put all this into context. For example, in the case that I just showed of the Nabateans, you could see that the largest concentration is towards east. And when we try to understand if this is connected, for example, to the actual equinox, we realize that this concentration is mostly due to a number of monuments that they are mostly related to the funereal, to the death realm. Okay, and we saw in some of the inscriptions that this is mostly connected to the months where the tombs are supposed to be open, and this is mostly in the month of Nisan. It was inside of the calendar, the Nabatean calendar as well. So this was not a solar connected item, but it was mostly a lunar month. So we are seeing that we need to nuance this. This is not a solar, it is a lunar concentration, while the ones on the solstices, they are connected mostly with other type of cultic monuments that they had to do with kind of temples to the kings and queens, that they are mostly, in these cases, connected to the sun. So we could start to see the differences as well, what connected with what the ethnographic, in this case, ethnohistoric information is telling us, which is very difficult, of course, because it's Roman and Greeks telling something about somebody else. From the point of view of the Roman and the Greeks. And you need to compare this data. In any case, I completely agree with you that if we only take the orientation, like for example, in the recumbent stone circles, we are going to have something that of course, it's telling us that this is significant, but the interpretation is going to be less reliable than if we have other sources of information. Completely agree.
No, 100%. And that's the challenge when we don't have any ethnographic or historical information. You can't go off of anything else.
Yeah.
So that's great. Anybody else have any other questions? Anybody online?
Yeah, can I just jump in real quick? I did have a question for you.
Yep.
Just just a fair bit earlier on, I believe it was when around the null hypothesis testing.
Yes.
You had it where it was if P was less than 0.05 was the point where you would mark it as being unrelated. How did you choose that as the point where it comes off from?
Yeah, very good question. Out of tradition.
Okay.
Look, this was a limit set by statistician in the early years of the 20th century, when he said, okay, if I have 1 in 20, then I can say that this is out of chance. 1 out of 20 is 0.05 probability.
Hmm.
So this is the 1 out of 20. Of course, this limit is up to you in a sense. Okay, you can say instead of 1 out of 20, I could say 1 out of 100 or 1 out of 1,000. Look, the 3 sigma, for example, this one in 20 would be something like 2 sigma limit. Okay. In natural sciences, anything that is or anything that was, so to say, as I said, this is something that needs to be a little bit nuanced nowadays. But anything that used to be below the 3 sigma level, it would be unreliable. Even when you now come to, for example, particle physics or cosmology, anything that is not 5 sigma is not reliable. Okay, so it's a little bit dependent on the field. For example, in humanities, we tend to say, okay, 1 in 20 normally is enough to have something that is telling us, okay, there might be something. Okay, but the limit is it is where the issue now it is within statistics, because many people is looking more at the limit than at the actual data, how the data behaves. If it is just slightly above or below this limit, then I can accept or disprove this null hypothesis. Well, maybe not so. I mean, it depends also on the quality of your data and so on. So this is why the limits now tend to be a little bit more, the people tend to be a little bit more skeptical on these limits. Okay, and this is why usually now you are asked to provide your p-value. For example, if not just that your p-value is less or more than 0.05, but also tell you, okay, my p-value is 0.001, for example. Okay, so it's telling you more on the data if you give the actual p-value. And then, of course, you set the limit before, you know that. This is what I meant when I said that you need to be fair to the data. Your limits need to be there beforehand. Okay, I'm going to trust anything that is above or below these limits. Then you do the calculation. And if it is above or below, fair enough. But you provide both your limit and the p-value.
That's very good. That's very informative. Thank you.
Can I ask a quick follow-up on that?
Yep.
If that's all right. Cesar, I guess you're talking about p-hacking here, about fashioning after the fact the significance. But I just wondered, historically, we're talking about how it was a matter of tradition, I assume in different disciplines. Was there any kind of empirical follow-up to show that it was 95% accurate all the times that something was accepted for significance? Is there some sort of magic chart of data out there that backs that approach up? And is that part of why it's been questioned now to say, well, we've agreed on a 5%, 95% confidence interval all this time, but in fact it isn't when you think about it, not all that supported by actual data.
Yeah, it is exactly what you said at the end. It was more something that it was building up in the last say decades, that people got more worried about these limits and why these limits were set up in the first place and why they've been used for so many times to say, okay, this is we need to reject this hypothesis because it is just a little bit above the p-value, or it is a little bit below, and then we accept it. And then we look, this in our case, it doesn't damage anybody if you set the limit here or here. But imagine if you are testing some medicine and you set the limit, and your limit is not very well, and you're set, and you're not very careful with the data, then you get into troubles. So this is why people have been building all these cases and trying to be very careful with the statistics nowadays.
Yeah, no, thanks. I was thinking about randomized control trials when you were talking about that, and the sample sizes make it problematic as well often. So, yeah, I can see you need to be especially careful. Thank you.
Well, Cesar, thank you so much for getting up so early in the morning and coming and talking to us and teaching us for 2 hours. So can we give a round of applause?
Absolutely. Thank you.
Thank you.
We have recorded this, so I will get it all put together. I've had the AI companion, so we can give some notes and things on it and transcribe it. But I'll get that all together and send that around, and I'll put the video up on YouTube over the weekend.
Okay.
Thank you so much again. I really, really appreciate that, and we'll do what we can to return the favor. But yeah, thank you so much.
No, thank you for the invitation, as I said.
All right, thanks, Cesar. We will chat again soon.
Yep.
Yeah.
Thank you. Bye.
Thank you. Thanks so
Bye.
much.
Have a nice time. Bye.
Oh my God.